All right, we need a few more tests to cover those inconclusive results that we would get, like when the ratio test would come out to be, equal to 1, or so we need some of these extra ones. All right, first one is called the integral test. Okay, this is not the official, I'm not going to say it officially, I'm just going to say this. If it looks like something you could do an easy antiderivative of, like 1 over n, okay, then this test works really well. Okay, so if it looks like something you could do an antiderivative to, the integral test it likely will work really well. This comes into play when the ratio test is inconclusive, or one of the other ones you've tried is inconclusive. All right, so here we go. If the integral from the lower bound to infinity of f of x dx converges, then the series of f of x dx as b and goes from b to infinity also converges. Hi. Awesome. There's an envelope right there. You can put it right on top. Thank you so much. And if the integral from b to infinity of f of x diverges, then the series also diverges. So as the integral behaves, so does the series. Oh, I don't know, because Mr. Pettis walked in and I just got distracted. But I forgot it right there. Okay, so as the integral behaves, so does the series. If okay, f of x must be continuous. Okay, so if f is discontinuous, this doesn't work. F of x must be positive. In other words, it can't cross the x-axis. And f of x is decreasing. In other words, approaching the x-axis. All right, so it has to be a function that is continuous and all in quadrant 1. It could be in quadrant 2 or 1. It has to be above the x-axis, and it has to be going towards the x-axis. Not necessarily. Okay, so maybe I should have written that first, but that sort of is the caveat. That has to be true. It's like the mean value theorem doesn't hold unless f of x is continuous and differentiable. Okay, all right, so let us embrace that with a box. Okay, but basically, if it looks like you could integrate it, you should try. So here's an example. The series of 1 over n rad n as n goes from 1 to infinity. All right, that looks like it could be integrated. Okay, because it's really just the same thing as 1 over n to the 3 halves. It's the same. So if we think maybe we want to try the integral test on this, we just got to think. Okay, is this a continuous function from 1 to infinity? Yes. Okay, is it positive? Okay, as long as you're going from 1 to infinity, it is. And is it decreasing, heading towards 0? These are cube roots. It's a square root function of something cubed. Okay, is it decreasing, terms that are decreasing? Okay, all right, so therefore we can try the limit test. So let's take the limit going. Okay, all right, 1 over n to the 3 over 2 dn. If you don't like that, you can change it to x or use whatever variable you prefer. And so we learned how to do properly integrals with bounds that are infinity. Oh, she's remembering. All right, so, okay, the limit, as that upper bound approaches infinity, use whatever variable you want. Sure. Okay. All right, we can do the antiderivative right now. Okay, what is the antiderivative n 1 over n to the 3 halves? Okay, because it's, remember, this is n to the negative 3 over 2. So raise your power. So it's n to the negative 1 over 2 times negative 2 plus our constant c, going from bounds of 1 to b, you guys decided. All right. So this would be the limit as b approaches infinity of negative 2 over the square root of b minus plus 2 over the square root of 1. So what do we get? 2. So the integral converged to 2. Does that mean that the series will converge to 2? No. It will converge. We don't know what it'll converge to. We haven't proven that, but it will converge. So basically, this is saying this area, if the area converges to a number, to a value, then the series will also have convergent behavior. Not the same necessarily ultimate value, but the same resulting behavior. Yes?
The integral of that is infinity.
Okay, so let's try another one. Integral test again. Okay, so the integral from 1 to infinity of, I mean the sum from 1 to infinity of 1 over 3n plus 2. I feel like I didn't finish the first, I didn't write converges. Okay, all right, so this really looks like integral test would work well. Okay, you still could try the ratio test, you could try the nth term test, you could try other tests. The ratio test on this one happens to be inconclusive. Okay? Okay. If it's more than 1, you can reach a conclusion of divergent. If it's less than 1, you can reach a conclusion that it's convergent. If it's equal to 1, you can't tell if it converges or diverges, so you would need something else to be sure. All right. So what? Geometric, if the ratio is between negative 1 and 1, it will converge. Equal to 1, inconclusive. Similar to the ratio test. Okay, ready? So we're going to try the integral. Oops. So our integral from 1 to infinity of 1 over 3n plus 2 dn will be the limit as b approaches infinity of the antiderivative. Okay, antiderivative is natural log of the absolute value of 3n plus 2 times 1/3 plus c, going from 1 to b. Okay, so this gives us the limit as b approaches infinity of 1/3 of the natural log of 3b plus 2 minus 1/3 of the natural log of 5. Equals what? Correct. Therefore, the integral diverges and the original function diverges. However, I neglected to check. You got to state when you're doing it like an FRQ proof or something. Okay, you got to state it's continuous, it's positive, it's decreasing. So f of x is continuous, just like you would if you were using the mean value theorem. You have to say it's continuous and differentiable. Therefore, the mean value theorem applies. So you say it's continuous. This is a hyperbola. Okay, 1 over 3n plus 2 is a hyperbola. It's continuous, it is positive, it is decreasing. You should know what a hyperbola looks like. It goes down like that. That branch of a hyperbola. Okay, it is continuous, it is positive, but the values of the terms are going down. Yep. So, since f of x is continuous, positive, and decreasing, the interval test can be applied. And then you proceed to do the integral test. What, Megan? And tests. Yes. Now, you don't do it on your homework every single time. No. Okay. But, yeah, anything that that'll be part of the points. Like if it says justify your answer, right? I mean, if it's multiple choice, no. Okay. But.
Did you say in ratio test that thing was inconclusive?
What was inconclusive?
The function was inconclusive.
Yes.
But if it's like
the result of the ratio test was 1.
So it was inconclusive. But didn't you say if the integral diverges, the sum also diverges?
Right. So we just proved it. We couldn't have told that from the ratio test, but we can tell it now by the integral test. Okay, let's keep going. Another one. No. Well, this one leads to 2 other subtests, but they have their own name. Okay, this one is called the P-series test. It's a corollary to the integral test. It's like a sub-case in certain cases. All right. All right, if you are given a series in the following form, 1 over n to the p, this is like the first example that I did for you. Okay, this happens a lot. In fact, it happens so much that you're going to do 1 over n to the 3. We did 1 over n to the 3 over 2. Okay, this happens so much, and you could every single time prove it with the integral test. But because it happens so much, they give it its own test, and then you can say, because of the P-series test, I don't have to go through all the work of proving the integrals. Okay, but it comes from the integral test. All right, so if that satisfies the conditions of the integral test, okay, so in other words, positive, continuous, positive, and decreasing. We can basically bypass the integral test and jump right to the p-series test, just saving us time. All right, then the series will do the following: converge if p is greater than 1, or diverge if p is less than 1. Okay, some teachers don't teach this test. They just want their students to do the integral test every single time. Okay, which is fine, it works. Okay, it's like some teachers don't teach, I don't know, sure. Right. They make you do something that would work every single time. Or they don't teach factoring. They just figure the quadratic formula works every time. Why would you learn factoring? Okay. All right. But, so the integral test does work every single time. But you are allowed by the College Board to cite the p-series test without having to skip, and you can skip the work of the integral test if you notice it in this form. And so we could have cited this for the very first question, according to the p-series test. Okay, so because the power in the denominator has to be in the form of the denominator was greater than 1, it will converge.
So the power can be decimals?
Yes, the power can be decimals. Okay, the power could be e, the power could be pi, as long it doesn't have to be an integer power. Isn't that great? It works. Okay, all right, so let's try one of those. Just show you what it looks like, because it may not look like it right off the bat to you. So for example, something like this. N going from 1 to infinity of the square root of n over n cubed. Okay, so yeah, you don't want to integrate that. Okay, but if we could, reformat that to apply the p-series test, yeah, it's just, if we said, oh yeah, this is n to the half, this is n to the 3, therefore, to simplify that by combining powers, you could do 1 over n to the 5 halves. So if you recognize it like that instead, oh, now I can do the p-series test.
Is it just like
N to the half times n to the negative 3 makes n to the negative 2.5, which is 1 over n to the 5 halves. Subtract your powers.
Oh, okay.
Right? Subtract your powers. See, it was a good thing we did that one. Okay. All right, so this satisfies the p-series test. Well, assuming it meets the conditions. So, is this continuous? Yes. Positive? Yes. Decreasing? Certainly. All right, so because it does all of that, since...
Wait,
Yes?
so wouldn't it not be continuous at 0?
We're not worried about 0 because we're going from 0 to, or 1 to infinity.
Okay, so oh, I see, okay, I see now.
Yep, and our lower n is 1. Especially, yes, because most of these have the denominator, and you can't have 0 in the denominator. Yes?
I think the test is kind of flawed because
Sure.
if
Okay.
p is less than 1, then it will be increasing. Then it doesn't meet the condition, then this test will fail.
If p is less than 1,
Yeah. So it will become
what if it's like,
like a half.
what if it's like 0.8?
Yeah. So
What if
it will
it's
become
negative?
a divergence. But if it's negative, then still increase. Oh, because if it's...
Then we haven't satisfied the hypothesis of it, so you wouldn't use it.
which is what you said
Then we don't need the second part. That's why you
I don't, so then only use it for convergence.
Why do we put it on there?
I don't know.
What? Who came
I
up
just
with
did.
this?
I don't know.
The person doesn't even put their name on the.
All right, well, Bobby, do you have any other questions about that? Because what haven't we covered then?
Yes, the second.
Right, we haven't covered it equal to 1.
Base 1, don't you just solve it? It should diverge. Because it's 2 to 1, so you don't need that one. There is one case in which
You're about to explain to us.
I wanna get through
that.
that.
Constant. Okay.
Oh, shoot.
So our question about P series is, what if P is actually equal to 1? If P is equal to 1, then it's just 1 over n, right? All right. This one is so common and so famous, it gets its own name. Okay, what are the terms of this? Like the physical terms. We went through and actually started by brute force plugging in, okay? 1 plus 1/2 plus 1/3 plus dot dot dot. Okay? This is called the harmonic series. All right, so it has a name. And so now we can cite, oh, by the harmonic series. Okay. All right, so what does the harmonic series do? Does it converge or does it diverge? Okay, what do you think?
It diverges.
It does. It diverges always. Okay. I will show you. Okay. So let's consider a different series that doesn't have a name, but I want to show you that series instead. So consider, you want to know why? Pull out only the terms that are powers of 2. Okay. All right, so the first one is 1, because that's a power of 2, because 1 over 2 to the 0. What's the next one? Okay, what's the next one? Okay. Okay, plus 1 not 6, 8, plus, oh, we ran out of time. Whoops, skipped it. I wrote 8 twice. All right, so we'll finish that tomorrow. You just have to trust me on why that the harmonic series always diverges. Okay, now, one other thing you have to know for your homework is the alternating harmonic series. That means if every other term is minus, that converges.
Wow.
So with all the positive terms, it diverges, but with alternating, it converges. Okay? So we'll prove that. We didn't quite get to proofs.